answer example number 1, chapter 29.
Termites are like sticky stuff. Does it stick to them?
It'll stick to the wall.
Like a sticky fireball.
It looks like on fire,
Mhm.
a stick.
Yeah.
Termites not that.
So we
Termites
have
like this.
this.
It's like the sticky grenade,
No,
like
that-
bees.
No, that's a Semtex.
Oh, Semtex. Okay, sorry.
And same as before, we have like a bar over here like this. There's a resistor here. The length of the bar is L. We'll just call it L. So it reads, a metal bar of mass M, so the mass of this bar is M, the length of it is L, slides without friction, no friction, on two parallel conducting rails a distance L apart. A resistor is connected across the rails and a uniform magnetic field pointing into the page fills the entire region. There's a uniform magnetic field pointing into the page. Okay, all over the place. I mean, I can just draw a few of these, I guess. The entire page. So this is B external. I'll just call it B, and the X means into the page, and it's uniform. So notice how different this problem is from the one that I did. The one that I did a little while ago, I grabbed it and I pulled it so that I pulled it at constant speed, right? Here, what we do is the following. If the bar moves to the right at speed v, let's say it's moving at some instant of time at speed v, what is the induced current through the resistor? In what direction is the induced current? So that's essentially the problem that I just did, right? If this thing is moving to the right at speed v, what is the induced current at that instant? Well, again, you can say the magnetic flux is B dotted with A, which will be just B times A times the cosine of 0 degrees. And this is going to be B times A. And you can say that A, the area of the loop, is L times X, where you can call this distance X if you like. So we have that the magnetic flux is BLX. And the question is, what is the induced current, right? Yeah, the question is, what is the induced current? So that means that the EMF induced, EMF, do you prefer EMF or delta V induced?
EMF, because it's shorter.
It's shorter? Oh, okay. So this will be the derivative of that magnetic flux with respect to time, right? I'm not going to put the minus sign because I'll deal with that through Lenz's law, right? And so this will be dVt of BLX. So this will be BL dx dt. But this we said is the speed, right? So the induced current will be the EMF divided by the resistance. So it'll be BLV divided by R. what is the direction, right? Of the induced current. So, let me say up the bar. Well, it's going to be up the bar, correct? By Lenz's law, it will be up the bar. I mean, current is not a vector, but nevertheless we can indicate the direction of the current in the circuit. Right? But technically speaking, current is not a vector. Okay, are we good with the first question and the solution? That's essentially the previous example, right? So there's a current here. Equal to that in magnitude. And down the resistor. Next question. What is the magnetic force on the bar when the speed of the bar is v? What is the magnetic force on the bar? Magnetic force on the bar will be it's going to be the length of the bar times the current in the bar, which is the induced current, right? Crossing to the external magnetic field, right? So the length of the bar is L. Now, the current has a value of BLV over R, and it's up the bar, we said, right? Cross into the magnetic field, which is B, and it's into the board, right? So notice that the force of the bar is going to be B squared, L squared, V over R, and what is up cross into?
So,
Up cross into is going to be to the left, right? That's the question. That's the answer. Oh, it's actually here. If the bar starts out with speed v is equal to 0 at t is equal to 0, maybe I'll let you read it. Because it's a cool problem, I think.
Right.
So, part C, if the bar starts out with speed v naught, like the initial speed, right? At t is equal to 0. So at t is equal to 0, the speed is v naught. And it's left to slide. In other words, you don't pull it. You just starts like that. Imagine you grab like a hammer and you go, and at t is equal to 0, you go boom. And at t is equal to 0, you give it that initial speed v naught. And it's, you don't push it anymore, just let it slide. So it says that it is left to slide. What is the speed at a later time t? What will be the speed of the part 3 seconds later, 2 seconds later, 5 seconds later, 5 minutes later? So I'm not grabbing it and pulling it so that I force it to move at a constant speed. I just, grab like a hammer and I go, or a bat and I go boom, and I hit it. I give it that initial speed and I let it slide. What's the speed later on? Right? So that's the question. Which is really, the way it's phrased and so on, it's a question for Physics 185. Because notice that the force acting on the bar, depends on the speed. So that means that the acceleration is not gonna be constant. So, but it's simple enough that we can solve. I think it's this one. So, if I do this, the sum of the forces is equal to the mass times the acceleration. This is on the bar, right? That will be the acceleration of the bar. I have, once it begins at t is equal to 0, the speed is v naught, right? The only force active on it is going to be that force which is to the left. And the velocity is to the right. So the force is going to be, I'm going to take into account that it is to the left by putting in a minus sign. And it's b squared, L squared, v divided by r. And this equals m. But now the acceleration is not constant. So I'm going to write it as dv dt. With the condition that v equals v naught at t equals 0, right? That's the condition that we're given, right? So I have to solve that equation. Are we okay so far? Are we good? Yeah, there's only one force acting, and it's this force. So to the right is positive. I'm going to make to the right positive, so it's to the left, so that's negative, right? So what I'm going to do is this. I am going to bring the v down here so that I have dv over v. And I'm going to keep the minus b squared, L squared over r m dt. Rm looks weird. Maybe mr is better. I don't know, it's just a matter of taste. Yes?
I thought the condition was that the initial velocity was 0.
No.
No, he meant
You
like v0. so like
strike
v
it, and this is, you give it that
Oh.
speed at t is equal to 0.
Okay.
So it was 0 before you hit it, but then I hit it and it comes off, whatever I hit it with a bat or a hammer, and it comes off at v naught.
Okay. Thank you.
I thought the same thing.
And then, did I do that right? Let me stand a little bit away.
That looks-
T, V L squared. Yes, are we good?
Yep.
Notice that I did this because then I have the variables having to do with speed on the left. I have constants over here and a dt by itself over there. So if I integrate both sides of this equation, next, if I do this, and all of these are constants, right? The magnetic field stays the same in magnitude everywhere, the length of the bar is the same, the mass of the bar is the same, and the resistance is the same. So I'm gonna do this. And the integral on the left is with respect to our variable.
v.
So I'm gonna have from v something to v something, right? So how about I say this is from v naught, which is the initial speed. And the integral on the right hand side is an integral with respect to our variable,
T.
t. So this will be the instant of time. I gotta match that lower limit on the right hand side with this lower limit on the left hand side. So this is the instant of time when the speed is v naught. What instant of time was that?
0.
At 0. And then this is the time. This is so many seconds later when the speed is that. So I'm solving for this as a function of this. But this is yes? But this is not a difficult integral to do, right? The integral on the left is what? What is the integral of the v over v? Natural log of v from v naught to v equals, and then I have minus b squared L squared mr. And what is this integral equal to? T, right? So this will be the natural log of V minus the natural log of V naught equals minus V squared L squared over MR T. And remember that when you take the difference of two natural logs, is the natural log of the ratio of the two things. So this is the natural log of V over V naught equals minus V squared L squared over MR T. And this is the natural log to the base E, right? Well, if it's a natural log, it is to the base E. It's really redundant to say the natural log to the base E, because if it is a natural log, it's to that base. But nevertheless, the argument, right, which is V over V naught, is equal to the base, which is E, raised to the thing on the right hand side. So it's E to the minus V squared L squared over MR T. And then the last line is the answer. The speed as a function of time equals the initial speed times E to the minus V squared L squared over MR T. Now, is this good? Let's check. What was the condition that we had, that we imposed over here? That at t is equal to 0, the speed was V naught. So if you evaluate this expression at t is equal to 0, what do you get for the speed?
V naught.
You get V naught, right? Because e to the 0 is going to be 1. 1 times V naught is V naught. So we're good. Right? And if you plot this, it's a function of time. Can I erase, I'm going to erase this now. Is that okay? Can I erase this?
Yes.
So if I do a plot of the speed of that bar, it's a function of time. This is t. That's the speed. It starts with V naught at 0, right? And then it exponentially, it decreases exponentially as time goes on. So it's going to slow down, it's going to slow down, and it's going to slow down, and it's going to slow down, and slow down, and stop eventually. We have a little bit of a problem here, right? Remember that I grabbed a hammer, and I went boom, and I gave it some initial speed. There was some kinetic energy, 1/2 mv naught squared. So I gave it kinetic energy. There's no friction here. So there's no dissipation of kinetic energy into thermal energy in the rails, because there was friction. But if this thing is going to stop, because as soon as it moves to the right, it'll experience this force to the left to keep it from sliding to the right, so that it doesn't increase the magnetic flux through the loop. So later on, it's going to stop. Eventually, if I wait a long time, it's going to stop. Where did that kinetic energy go? Where did the kinetic energy that I gave this bar go? Because initially there was kinetic energy, 1/2 mv squared, 1/2 mv naught squared, and then it stops. So there's no kinetic energy at the end. So what happened to that kinetic energy? I mean, energy is conserved, right? It must have gone somewhere.
Is it magnetic?
What did it
potential-
happen?
Magnetic potential energy?
What?
It turned into the current,
Into what?
into the current of the wire.
And
Magnetic field produced.
at the end it's gonna stop. There's not gonna be a current. There's not gonna be a.
And change in EMF. I mean,
Is there a dissipative element in there?
Heat.
Is there a dissipative element in there? The resistor.
That turned into
Right?
light.
So there's going to be current into that, going through that resistor, right? And if it gets hot enough, it'll give off light. If not, at least it'll turn into thermal energy.
if you didn't have a resistor, would it just be the other two factors?
No, then the thing is gonna, like, where is that energy gonna go?
And it wouldn't have anywhere to go. So would it make that force if it didn't have the resistor?
Well, there would be the resistance of the wire at some point, so.
It just take.
So how about we calculate, and this is the next question in this problem. Let me probably pose this. So the initial kinetic energy of the bar was, of course, 1/2 mv squared, mv naught squared, right? Where does this energy go? Prove that energy is conserved. And you have to account for that energy, right? In this process, by showing that the energy gained elsewhere is exactly 1/2 mv naught squared. So the dissipative element over here is the resistor. Do you remember the expression for the power dissipated by a resistor? What is the expression for the power dissipated by a resistor? What is it? I squared times R. Yeah, the current squared times R. So, how about we consider the power dissipated by the resistor, right? So, that would be part D. The, power dissipated by the resistor is, well, the power is I squared times R, right? But what is the current? The current is I think I erased it, right? I had the current. Actually, I have it right here, right? The current is B LV over R squared times R. So the power dissipated by the resistor is B squared L squared R times V squared, right? But wait a minute. The speed is changing, right? I mean, the magnetic field is the same throughout. It's everywhere, it's uniform, right? We were given that. The length of the bar is always the same, that doesn't change. The resistance.
Wait, Professor. Shouldn't R be in the denominator?
Oh, yes. Thank you. But I have a V squared over here, right? And that V is changing with time, according to this. So the power dissipated by the resistor depends on whether you're looking at 1 second later, or 2 seconds later, or 3 seconds later. Right? So let me plug that in here. So I am going to erase this, okay? So this is power, right? So this is B squared L squared V, well, over R, right? And all of this times the speed, which is V naught. I'll write it like this. And I have to square all of that, right? So this will be B squared L squared V naught squared over R times E to the minus 2, because that 2 then becomes part of the, right? Yes? So notice that that's a function of time. The power dissipated is not the same. But what I want is the energy. How do you get energy from power? What is the definition of power?
powers, isn't it energy per second?
Per second.
It's the energy dissipated per second, that's the power. So if I want to know the energy, then I have to multiply the power by time. The problem is that as time goes on, the power is not the same, so I cannot just multiply it. So guess what do you think we need to do?
Integrate.
I mean, normally you say power is energy over time, right? So you say, oh, if I want to know the energy, it has to be the power multiplied by time. But that is only true if the power, dissipated in the first second is the same as the power dissipated in the fourth second is the same as the power dissipated in the 20th second, right? So then you can just multiply it. If not, you have to do this. And then you have to say, the energy is the power times dt, and then you integrate. Because so you're guessing that the power is constant over an infinitesimal time, but then you keep adding the contributions to the energy for the different time intervals when the power is different, because the power is a function of time. So essentially you do this, and so the energy dissipated, this is the energy dissipated, total energy dissipated will be the sum of the energies dissipated in the different time intervals, because it's not constant, and that would be the power. So I'm gonna take this power here, and I have to put it in here, integrate from, well, this thing will eventually stop, right? So I'm going to integrate this from t is equal to 0 to t equals infinity. I'm going to give myself enough time to make sure that the thing stops. Because this is just exponentially getting slower. I'll just make sure that I take it to infinity. So that power is going to be all of this. I'll just say p dt, right? With that power being here. Can I erase that now? Because I want to do this integral.
Yeah.
And what do you think I hope to get? The total energy that's going to be dissipated by the resistor better come out to be 1/2 mv0 squared. Otherwise, either I made a mistake or energy is not conserved. Can I erase this? I guess I'm already doing it. So let's crack through this and have fun remembering our math teachers.
Fine.
So the total energy dissipated will be the integral of this quantity. All of these are constant, so I'll just save myself a step, but I'll just pull them out. Times the integral of e to the minus 2b squared L squared over mr t dt from t equals 0 to t equals infinity. All right, let's do this. This would be b squared L squared v naught squared over r. Now, what is this integral? What is the integral? What is the integral of e to the minus ax dx? For example, maybe you know it like this. Where a is some constant that multiplies x. What is the integral?
Negative a.
Negative who?
A.
You're taking the derivative, not the integral. So therefore, to get rid of that, what do?
E over.
You divide by it, right? So it's going to be negative 1 over this quantity, right? Which is 2b squared L squared over mr, negative of that, right? Times e to the minus 2b squared L squared mr t, evaluated from 0 to infinity. Right? This will be minus 1 over a e to the minus ax, right? That's what I'm using. So it's minus this, but I'm gonna bring the MR upstairs, right? I'm gonna bring the MR over here to the numerator. So that if I were to take the derivative of this, I would get that. Can I erase this integral here? If not, you can look it up. All right, so this U total equals, all right. So I'm gonna put a minus sign outside. I have B squared, L squared, V naught squared over R times this thing over here, which will be MR over 2B squared, L squared times e to the minus infinity, which is 0, right? Because e to the minus infinity is the same as 1 over e to the infinity, which is the same as 1 over infinity, which is 0, minus e to the 0.
Oh, is that t still in the?
Huh?
That t still in the exponent?
How do we get the t out of there? Or is it meant to be up there?
No,
I think it's
it's
meant
here.
to be up there.
Supposed to be up there. Thank you. I put it in the wrong place. Now, how much is e naught, e to the 0? 1. This is 0 over here, right? So notice that this minus sign cancels this minus sign. And then, let's see. I have a b squared here that cancels this b squared. What else can I cancel? I have an r here that cancels this r. Let's see, do I have other cute colors? And we have an L square here that cancels this L square. And isn't this BEA? Beautiful. This minus and that minus gives me a plus. I have a 1/2. I have the mass. And I have the V naught squared. That's the total energy dissipated by the resistor. Precisely the amount of energy that we put into the system when we hit it and we made it move with an initial speed V naught. It's cool, isn't it? Well, I thought I did this problem as an example. You know, there's this issue over here, right? If, you know, sometimes people, okay, so energy is power multiplied by time, but you know, this is only true if the power is the same for every interval of time. But what happens if the power is changing? Then you have to split it up into a sum, right? It's the power over this time plus the power over this time plus the power over this time plus the power over this time, right? And then you do the sum. And that's what an integral does for you. Anyway, it's a cool problem, which goes a little bit beyond the example that I did in class. I mean, that I did earlier today, right? On that. Questions?
Just real fast, so if you have the integral of e to the ax, that equals a e to the ax.
The integral?
Yeah, I just want to make sure.
This integral, e to the minus ax dx, is minus 1 over a, e to the minus ax.
Yeah. Oh, okay, over. Yeah, yeah, that makes sense.
Because what if I forget about this? What if I differentiate? What is the derivative of that? Minus a e to the minus ax. The minus a will cancel this minus 1 over a. I'll just get e to the minus ax, which is this.
Okay.
I mean, that's how I do it. I check by taking the derivative. Okay? You must know that integral.
Yeah.
Just like dx over x, you know, the natural law, that one, you must know that integral. It just shows up, you know, there are a lot of problems where you have an exponential behavior, so it's an integral that's worth committing to memory. Can I erase this now?
Yes.